Okay, so this lecture, I just pressed the record button. This lecture will be about implicit functions, what they are, and how you can do stuff with them using math. But first, let's talk about what is an implicit function. So here are my slides on that, which are available on Blackboard, of course. And I asked people if you already know what an implicit function was, and nobody said anything, but I bet some of you already do. The word implicit is related to the word implied. And it's the fact that even if a function isn't written in its normal form, there is still an implied function going on. So let's talk about what a function is, what's an explicit function, and what's an implicit function. Okay. Let's first talk about what an explicit function is. It's something that can be written, let's say, y equals f of x. That means y is a function of x. That's one way to read that. Y equals f of x is how I would actually read that is y equals f of x. But what it means is there's some variable y, and it can be written as an explicit function of x. That's kind of what we think of when we think of functions. For example, y equals x squared plus 2x plus 1. This is explicit because only y appears on the left side of the equation. In fact, exactly y appears on the left side of the equation. And on the right side of the equation, there are only x's and numbers and whatever else, but it's some function of x. So y equals some function of x is an explicit function. By the way, I don't think I put this on this slide, but something about a function is that it has to only equal one thing. I feel like drawing this. I feel like drawing it, and so I'm gonna draw it. Sorry, let me remember. Here's a whiteboard. Share. This is poorly drawn y-axis, and this is a poorly drawn x-axis. And you have some function in red. This is okay, right? This is a function. What if it goes up and then like, oops, goes like this and then goes this way? That's bad. You can't have a function that does this. If this red line here were f of x, what's going on here that I'm saying is bad? It's that you can see some points here where it's actually like three things. Look at this, x star. The question is, what is the value of f of x star? This red curvy line is really failing at telling you what f of x star is. Is it this point? Is it this point? Is it this point? Is it all three of the points? So what I've just drawn for you is actually not a function. I can make a little and a Family Feud bat sound, because it fails this very important property, which is that you give me any point, let's call this point here x star, it should be able to tell you, well, if x star is included in the domain of f, the domain just refers to all of the numbers that can be evaluated using this function f. If x star is in the domain of f, then it should identify exactly one number, and that's the function. And this fails it. I think this is a very clear point that I'm making here. It can't have this like multiple values for one point. Okay. And that's an important criteria. That's an important property of a function. By the way, there are things like this that can exist. They're just not called functions. They're called correspondences. So if you have something that takes a value as an input and gives perhaps multiple values as outputs, that's no longer called a function. It's called a correspondence. And of course, they exist in the mathematical world, but we economists generally don't have to worry about that too much. We care about functions. So what I've drawn on here, remember, is not a function. What would be a better something that's a function, that's good because it never, you can tell each, and it never violates this. You might call it like a vertical line test. If you could ever draw a vertical line and it goes through, the function goes through that vertical line more than once, it's not a function, it's a correspondence. Okay. I've made that point, probably too much. Let's go back to my slides. Why is it here? Okay. One current slide. Here we go. Anyways, anything so you can write this way, y equals f of x. Here, f of x is x squared plus 2x plus 1. That's what f of x is. You can tell right away that I could put one value of x in there and it would give me one value of y. It's a good function. But what about functions that aren't this explicit, as y equals something? For example, you could have an equation that has y's and x on both sides, like this, even though this equation actually only has the x's and y's on the left, but that's okay. Here's an equation, x squared plus xy equals 1. And I'm just so used to annotating now. I like this. You take this equation, it sort of highlights what I'm talking about. And you notice, well, I don't have y equals something and some function of x. You actually have them all mixed together. It still describes a relationship between x and y. There's a certain relationship between x and y that's implied, thus the word implicit, that's implied here that says, for example, I thought I should have made this, not the question and the answer appear already on the slide. I could have used animations to prevent that, but I didn't. My apologies. But for example, in this, if I said, let x equal 0, what does this imply about y? There's that word imply again. And I think you could answer that. If x equals 0, then this becomes 0 plus, this is 0 times y, that's 0 because x is 0. The y remains y squared equals 1. I actually had that written already. I actually had this written down here. The question is, what happens when you let x equal 0? You get y squared equals 1, which you should know has two answers, which is plus or minus 1. The square root of 1, both positive and negative, is 1, plus or minus 1. So this relationship that I've circled, and I'm circling again, multiple times I'm circling it, it is a relationship between x and y. But is it a function? Sort of hard to answer this, because functions have to have this, they have to have this property where you give me one x, it'll spit out one y. I think you can see that that is not true, because if x equals 0, you don't just get one y that satisfies this equation, you get two y's. Y could be 1 or negative 1. So it's not, in the normal sense, a function. However, we can still say it is an implicit function of y and x in the region. Okay, so let's say we're at the point x equals 0 and y equals 1. If we're at this point, we have this relationship between x and y described by this equation. And it makes sense when you're near this region with x equals 0 and y equals 1. It actually does look like a normal looking function. It would pass this vertical line test because we would ignore everything that's going on further away. So what I'm talking about now is a neighborhood. We've like zoomed in, you got a real close neighborhood of the point x equals 0, y equals 1. You might say, well, what about that other point? That point x equals 0, y equals negative 1. And I would say, oh, that's outside the neighborhood. Forget about that point. Right now, we're just looking at x equals 0, y equals 1. And actually, this would be a function there. Y and x would have this relationship of what's going on like that at that function. I'm sorry, at that near that point. There could also be one near x equals 0 and y equals -1. And so that's what we're going to maybe see in today's lecture, is that this implicit function actually, it is an implicit function. It's an implied relationship between x and y. Is it the same as an explicit function where y equals some function of x and it's uniquely determined for every x? Or, sorry, one x uniquely determines a y? That is not the case. So we're going to hopefully start to see when we can do this and say, let's take this implicit function and think of it as an explicit function, at least in a neighborhood. When is that possible, and what are the consequences of that? But okay, hopefully what this slide was really about was just demonstrating the differences between explicit functions, guys that look like this, guys that look like this, and implicit functions, guys that look like that. I need to clear all my drawings because they're certainly getting in the way. Okay, you have any questions about that? I mean, let's be honest. The easy way to tell is, are the x's and y's mixed together? If they're mixed together like this, it's implicit. If they're separate like this, it's explicit. That's probably the easiest way to tell. Next slide. Here's some more examples. Here's a question that I actually am asking. If you want to help me, that'd be great. Let's say x squared y minus x over y squared plus 1 is equal to the quantity x minus y cubed minus 1. I gave you a more complicated function this time. Excuse me. Pardon my sneeze. This is already, you can tell this is an implicit function. Y can be described as an implicit function of x just using this equation. How do I even know that? How is it that I can just look at this equation and say, yes, there is a relationship between x and y that's being described? I won't make you answer that unless you want to. I'll just tell you. The relationship is, this equation tells you I could take any x, I could take any y, I could plug it into this equation, and if it's true, then x and y, that combination of x and y, are somehow legal. You know, they are part of this. That's essentially, that is the relationship. A point x and a point y are related in that if you plug them into this equation and it holds, they go together. Whereas if you took an x and a y, you plug them in this equation and it doesn't hold, they don't go together. So at the very least, knowing nothing else, this is an implicit function of a y and x, because it's just an equation. It's a relationship between it. Okay, let's go a little further. In this example, if x equals 0, what is the value of y, which is implied by this implicit function? I think we already did an example like this, but let's just think about it. If x equals 0, this first term becomes 0, right? Minus 0 over y squared plus 1. Well, you know that this is the denominator is never equal to 0, because anything squared plus 1 will be positive. We can't have imaginary numbers yet. We're not even speaking about imaginary numbers. So this is definitely positive. And in fact, 0 over something positive is 0. Minus, okay, x equals 0. So this is 0 minus y cubed. Minus 1. What is the value of y, which is implied by this as a function? I don't know. Why don't you get negative y cubed here, move it to the other side. Y cubed equals -1. I think the answer is y equals -1, right? So this actually satisfies the vertical line test, where if x equals 0, there's only one value of y, which is implied by this function. That's y equals -1. But the point is there. The point is this is just like a function, even though it's not written as y equals f of x. And actually, you would have a very hard time writing that as y equals f of x, wouldn't you? If you tried to solve this for y, what would you even do? What would I do? My goodness. I guess I would maybe expand this cubic term. You would have x cubes and x squareds and y, x, y squared and y cubed terms. Multiply everything through by y squared plus 1. So you would have a y cubed times a y squared term. You'd have a y to the 5th term here. But basically, this is polynomial in y. It would be a y to the 5th polynomial, and you'd have to solve that, which would be very difficult to do. But in theory, it'd be possible. I'm not asking you to do that. I just want you to see that in theory, it would be possible to do that. Clear my drawings. I think I have the answer. Oops. Oh, I didn't put the answer on it. I guess it was easy. The answer is y equals -1, right? Okay. Now let's talk about formalizing implicit functions as equations. By moving all terms to the left side of the equations, it's possible to write any, I love annotate, any implicit function as an equation. There's no like, but wait, what about this? But wait, what about this? This is just a simple fact of algebra. When you have an equation, if you want to, you can move all of the terms to the left side of the equation. Simple. Just, if it's positive on the right side, it becomes negative on the left. If it's negative on the right side, it becomes positive on the left. But literally any equation, including the one from the previous one, can be written in this form. Notice I use capital F here, and not just me, but the book uses capital F here when talking about implicit functions. I think it's just to remind you or anybody who's reading what you're writing, me, perhaps, that this is not an explicit function. This is an implicit function, and it can have as many variables as you want. Remember, this is like the most common way to denote an uncertain or an indeterminate number of variables. How many variables are there? N. What are their names? Oh, x1, x2, ... xn. That just means that there's an arbitrary number of variables altogether and on the left side of the equation, and you can always write that as capital F of those n variables. And it could always be made to be equal to 0. You might say, well, what if there's a 1 on it, like this? Look at this one. What if x plus y squared equals 1? There's no variables on this side, and it's not 0. Just subtract 1 from both sides. Okay, fine. That -1 could be part of f, right? It doesn't have to be f of this equals 1. It can always be f equals 0. And if you have a 1, just move it to the other side. Okay, so far all I've said is that you can write an implicit function this way. All right, this equation may or may not actually be solvable for any given value of a variable. Thought about that? This could be weird, right? You guys have any questions, by the way? How's my pace? Keep going. Let me know if you have any questions. This could be very simple. I'm not sure for many of you, but think of this equation I just said: x squared plus y squared minus 1 equals 0. That's an implicit function of x and y. What if I said, okay, if x equals 2, what does this imply about y? And the answer is there is no real solution. This implicit function is basically not defined for x equals 2. It doesn't exist. It doesn't. At least there are no y's that exist that solve this equation, and therefore the implicit function does not exist at x equals 2. Is that okay? You probably, this happens, by the way, this happens with explicit functions also. If I said y equals the square root of x, and I said, well, okay, then what is y? If x equals -1, what's y? Your answer is, well, there's no real number. Once again, then we'd be talking about imaginary numbers. Same thing with logs. You try to take the log of a negative number, it doesn't exist. Although actually it's negative, it's imaginary once again. Okay. Next point. If the equation is continuous means little change in x corresponds to a little change in y, and they're on big jumps. And it can be solved at some point, right? It should be solvable somehow. Then we can say each variable is an implicit function of the other variables in a neighborhood of that point. And this is important. I brought it up earlier in the very first slide of us talking about implicit functions. I brought up this point that unlike explicit functions, which exist really just, the x-axis you could think of as the domain of the function, and the y-axis is the range of the function. And that's even true even if there's more than one variable in the domain. The domain could be multidimensional, but still you have this idea that you take any element in the domain of the function and it spits out a unique number in the range of the function, domain to range. That's true for explicit functions. And you don't have to specify, wait, what neighborhood are we in? However, for implicit functions, you do have to specify what neighborhood are you in. And this function that I've written on the slide is the perfect example of that. It's not perfect, it's a simple example of that. X squared plus y squared minus 1 can be solved at the point 0, 1 or the point 1, 0. So in a neighborhood of each point, each variable is an implicit function of the other. Okay, this is a continuous function. X squared plus y squared minus 1 equals 0 is continuous. It's solvable at the point 0, 1. It's solvable at the point 1, 0. Those are both places. By the way, you guys know this is a unit circle, right? This is a unit circle. And new share, whiteboard, share. Because it's a unit circle, clear drawings. Can I actually draw a circle with my thing? Oh yeah, that's way better than I could do if I were trying to draw it myself. And this is good because I'm going to need this. Let's try to do some axes here right at the halfway points. Here's the x-axis. Oh wow, look how good this looks. We can thank the Zoom whiteboard editor for this. Okay, so there's a point here on the slide. I talked about 2 points. There's a point here at 0. This is 1, 0, and this is 0, 1. Might actually add some text to this. This is the point 0, 1, and down here is the point. You're comfortable with this notation. I write the x-axis first and the y-axis second. And this is the function x squared plus y squared minus 1 equals 0. It's the implicit function right now. That's what we're talking about. Gosh, I should just write that in the text too. F of x, y equals x squared minus, no, not minus, plus y squared minus 1 equals 0. Okay, that's the implicit function that we're drawing. And oh, by the way, there's really any point on this circle, we could zoom in and think of it, okay, this is an implicit function defined in that neighborhood at that point. How do I know? Because it's continuous. If it had a jump to it, we might say, oh, actually the function's not defined at that point, but there's no discontinuities. So we could think of what's going on here, implicit function, perfectly fine. What's going on here? Implicit function, yes, there is an implicit function because there's a relationship between x and y that's implied at that point, okay? But we'll come back to this. There's a reason I spent a minute drawing this on Zoom, a whiteboard, because I know I'm going to come back to it soon. So let's leave it. It should still be here when we come back to it. Sure. Where does it go back to here? No, there we go. Okay, done with this slide. This slide is really about how to formalize an implicit function as an equation. What? I didn't do that, did I? Current slide. Okay. Here's my next slide. When do explicit functions exist? I've already said that the implicit function exists for any point on that circle in any neighborhood. And take any point, you have a neighborhood nearby that has a relationship between x and y. It's well defined. Well, we have something called the implicit function theorem, which tells us when it is possible to write one variable as an explicit function of the others. By the way, when I say when, I mean given some implicit function, when is it possible to write one of the variables as an explicit function of the other? That's the question here. And it's called the implicit function theorem. It says, I'm going to, I think if you look in the book, it might depend on which book you look at. If you look at the Sid Sayer text, I think it does only talk about a few variables. But if you look at the Chang and Wainwright text, it will definitely say arbitrary variables, x1, x2, ... xn. I think I'm going to just do the xyz for this class, pretty much from now on. And the reason is, even though I want you to be able to abstract what we're doing to arbitrary numbers of input variables, I'm not going to ask you to do it on any quiz or exam to do more than 3. Like I don't think I would ask you to do f of x and y and z and w on a quiz or an exam. So because I'm not going to ask you those larger dimensional things, I'll just keep, even when I'm defining the implicit function theorem, I might as well just talk about, actually not 2. It's deliberate that I chose 3. And the reason is, I feel like if I had just included 2 here, f of x and y equals 0, that's the kind that's maybe easy to graph. It's 2-dimensional. You could think of that on a piece of paper, but it's somehow less economic in the sense that we want to talk about things with more than just 2 variables in economics. Why is that? Let's think about utility, for example. If I want to talk to you about utility, one of the most important things about utility is that it represents preferences. I would argue that is the most important thing about utility. The most important thing about a utility function is that it represents the preferences of a decision maker in such a way that if I can plug something into the utility function and it gives me a large number, and I can plug something else into a utility function and it gives me a smaller number, then I would prefer the thing that gives me the higher number over the thing that has the lower number. That is it. That is the most important thing. In some sense, the only important thing about a utility function. Okay. Why am I saying all this? It's because economics is about trade-offs, isn't it? Economics is about what would we choose given some sort of scarcity. Don't you agree? If you could always have as much of everything that you wanted, you would have no need for economics. Everyone just consume everything all the time, whatever they want. Who cares? No, it's not about that. It's about the fact that goods can be substitutes for each other. I want some of this, but I also want some of this, and there's a trade-off there. Or if you're a firm, I want to use a lot of capital to produce, but I also need some labor to produce, and there's a trade-off between those 2 things. So at the very, very simplest mathematical modeling of these types of questions with trade-offs, you need 3 variables. You need 2 input variables and an output, at least. So that is one reason why I want to write these with 3 variables. I'm not saying it's useless to ever talk about 2 variables, but it's very common. You might need to talk about something which can't be drawn on a piece of paper because it's 3-dimensional. Because there's 2 input variables and 1 output, and the function that would be implied is somehow 3-dimensional. Okay. So in general, I think I've decided in a lot of these examples, 3 variables is where I'll stop, where I'll go to and stop. Okay. Now let me just describe the implicit function theorem with these 3 variables. Let's say f is a function of x and y and z equal to 0. That's what we would call an implicit function. X, y, and z are implicit functions of each other. Now let's restrict f to be continuous and differentiable. Can't have any jumps or kink points where not differentiable. And let's say f has a solution at this point, x prime, y prime, z prime. The primes here aren't derivatives. These are just ways to like specify a specific point. Sometimes you could use star there. I guess maybe I was lazy or I was following the notation of the book to use a prime instead of a star. Either way, if you assume this, then it is possible to write x as an explicit function of y and z in a neighborhood of x prime, y prime, z prime if the partial derivative of f with respect to x is not equal to 0 at the point x prime, y prime, z prime. That's it. This is actually, it's a theorem that's almost like telling you when you can't do. I take it back. It's not telling you when you can't do it. It's telling you when you can do something. And it's not even telling you the only time you can. It's really just saying, if you can, if this is true, then you can write x as a function of y and z. By the way, how would you even denote that? How would you denote this sentence here? It is possible to write x as an explicit function of y and z. I would write that, the shortest way I could think of to write that is like this: x as a function of y and z. Right? You could write it that way. Although sometimes people don't like this, those all variables. And another way you could write that is x equals, and now not uppercase f, but lowercase f of y and z. Right. This is actually both of these are equally valid ways to write what I've written in this sentence. It is possible to write x as an explicit function of y and z. Okay. So you might say, what does this part have to do with anything? Why should we care about the partial derivative of f? Remember, that's the original implicit function there, capital F. We take the partial derivative of that with respect to x, and it should not be equal to 0 at the point x prime, y prime, z prime. That seems to be unrelated to whether or not I can write x this way. But actually, it's not. And I can hopefully go back to my 112. I go back to my blackboard. Actually, it's called a whiteboard. Go back to my whiteboard drawing that's still there, and we will see exactly why this is true. And it's exactly about what's going on at these 2 points that will highlight this fact. Okay. What does the implicit function theorem say? Let's say, can we, let me write that. I'm going to use text because actually text is better than me trying to write. When can we define y equals some function of x? That's the question. All right. When can we define y equals some function of x, given this implicit function here, this implicit function, capital F of x, as written out here? And the implicit function theorem tells us the answer is, I want to write on this again. Hey, what's going on? This is weird. I can't even like see what I'm doing. It won't give me, it doesn't give me options for the right. I don't know why it's doing that. Let me write. If I do this, does that do it? What happens if I start writing? Nope. My computer's acting weird. I'm going to stop sharing and then come back to share it. Maybe that'll do it, something. It allowed me to write the question, when can we define, okay, here we go, text, it's back. For some reason, it's back. The answer, but because of the implicit function theorem, is when I'd like to write, actually this part I'm going to write with my drawing tool, and that is when curly d f over curly d, is it y or x? Which one is it? What do you guys think? I'll fill in everything else. Curly df over curly d something should not be equal. That's a not equal sign, 0. So tell me what belongs here, y or x? And I will say this, in the past, I have also made this mistake, and therefore I have gained the wisdom to take a little bit of time here to think about what belongs there. Does anyone have a guess? Any thoughts? The question is, here's the question. When can we define y equals f of x? Answer, when the partial derivative of f with respect to blank is not equal to 0. Tell me what belongs in the blank. There's only two choices, x or y, so you have a 50-50 shot of getting it right. If you're right, I will heap a load of praise on you. You will feel good for minutes and minutes. And if you're wrong, you will receive shame. You'll be banned from class, and your children will be banned, and your children's children will be banned. I'm just kidding. None of that will happen. Lifetime ban from Econ 403. I don't think I'm allowed to do that. No one has a guess? Oh, geez. Is it because you don't know what the implicit function theorem is? Because I didn't leave it up long enough. Either that or no one can hear me. Can anyone hear me?
Would it?
Oh, yes, yeah. Jordan can hear me. At least one person can hear me speak.
I guess it's a 50-50, so would it be x then?
You think it's x? All right, let's think about it, okay? Thank you, Jordan. I was definitely kidding about the being banned thing, but even more so, even if you guess wrong, at least it's some sort of interaction. So I feel like I'm not just screaming into a black hole. Okay, thank you. Partial f over partial x not equal to 0. I'm not saying whether you're right or wrong, by the way. I'm just going to investigate. Let's take the partial derivative of f with respect to x. What do we get? Partial derivative of f with respect to x. I've taught you guys partial derivatives, so you should know how to do this. Remember, the equation here is x squared plus y squared minus 1 equals 0. I think you know what that is, right? 2x. 2x. So this says we need 2x not to be equal to 0. Okay. That means x could be 1, but it can't be 0, right? X is this point is x equals 0. That would violate this equation. X equals 1 would satisfy this equation. So what Jordan says is partial f over partial x not equal to 0 implies that we can define a function here. No. Yeah, we can define a function here, but not here. Let me do like little checks and x's for that, because I think that's I like this sort of consistency. Like this is the Jordan hypothesis. Do you mind if I name it after you? The Jordan hypothesis is we're okay over here, check, but we're not okay here, x. What do you guys think about that? Remember what I said about the vertical line test? Which place passes the vertical line test? Remember, now we're talking about y equals a function of x, not for some reason x equals a function of y. No, we're not talking about that. Y equals a function of x. When does that happen? Oh, by the way, it's important here that remember that inside the implicit function theorem is this little phrase that says in a neighborhood. What does that mean in a neighborhood? It's pretty vague. Like, how big is a neighborhood? Is it like your block? Is it your, is it 10 blocks? Is it the whole city, the whole county? Okay, that's real life neighborhood. In math, a neighborhood really just means any as small as you want, distance. Usually it's called epsilon, but it has to be positive. So it's just a small but positive distance around the point is considered a neighborhood. Small enough that anything that's happening on a larger scale is far enough away. So only what's happening locally matters. That's what a neighborhood means. Even my definition, as I'm saying it, still sounds vague, so I apologize for that. But really, you should think of it as, epsilon greater than 0 distance around the point. So you guys tell me, is the Jordan conjecture correct or incorrect? Does this point satisfy the vertical line test and this one not? Jordan, you say yes? Let's zoom in here at this point 1, 0. What would it look like? And I'm sort of going to exaggerate it.
Well, are we including the bottom half of the circle in the 0, 1?
Yes, we are. Yes, we are. Right? Because the whole black circle is the implicit function. It's the relationship that's described by the implicit function. It's the black circle.
Like, I guess I meant when we're setting x to 0, are we including y being 1 and -1?
Wait, x equals 0 is this point up here. Is that what you mean?
Yes. Would it also include on the lower end, y being?
Oh, okay. Okay. Yes. Well, so, no, those are different neighborhoods. I apologize. So here's what I meant. Remember, I defined this point and this point, and I said we're going to come back to these 2 points. You are correct. There is a point down here which we could investigate if we want. But for the purposes of this, I do not want to investigate it. Right now, all I want to say is there an explicit function y equals f of x in a neighborhood of this point? Yes or no? And is there an explicit function y equals the function of x in a neighborhood around this point? Yes or no? I agree that we could also be asking about this point, but I don't want to bother with that just right now. Okay, so here's our question. If this is our answer, partial of f over partial x equals, I hope this is not the thumbnail. By the way, I'm telling you that this answer is wrong. I hope this is not the thumbnail on YouTube, because this would be telling you something which is incorrect. And the reason it's incorrect, sorry, Jordan, I'm still glad you guessed. And your children's children are not banned. They're welcome to come to Econ 403 whenever they want. But it fails the vertical line test. If you think about it here, no matter how much you zoom in to this point, there's going to be I don't know if I can even draw it. I'll try, but let's get a line going on here. There's going to be this fact that it hits this line in 2 places. See this red line? It doesn't matter how close I get to this point. As long as I'm not right on the point, if I'm anywhere to the left of this point, it's going to hit this in 2 different places. And that's why we actually cannot define y equals a function of x at this point. It doesn't exist as a function. It exists as a correspondence. Remember the beginning of this lecture, I said, oh, by the way, if it fails this test, it's not like it's a horrible thing that we should destroy. It's called a correspondence. It's not called a function. But anyways, there is no function of y, there is no way to write y as an explicit function of x in a neighborhood of this point 1, 0. Wouldn't you agree? I mean, you could define it only going up from the point 1, 0. That would be okay. Or only going down from the point. That would be okay. But that's not a neighborhood. A neighborhood has to include all of the points nearby the point you're talking about. So that's why this is actually an important idea to say. In a neighborhood of 1, 0, there is no explicit function of y as a function. There is no explicit function y as a function of x. Does that make sense? Whereas what if you tried it here? Of course, anywhere here it would be fine. There's no way that you could draw a vertical line here and it would violate. It would cross two places. Now you might say, well, what about this point down here? If you drew it here, it would go all the way down here. That's not a neighborhood. That's not a neighborhood of 0, 1. That is a place, that's a global effect somewhere else. And I don't really, even after talking about it for a few minutes now, it's hard to give a great definition of what makes something a neighborhood. But you just need to think of it as like if I zoomed in really, really close, but still allowed some positive distance around the point 0, 1. What would that's what you should think of as a neighborhood. And don't worry about the fact that, oh, by the way, it has to cross down here too. That's outside the neighborhood. Whereas here, doesn't matter any distance you get close to this 1, 0 in some neighborhood, it's going to cross the line twice. And that is the problem. So that's why we need to fix this. Undo. Can I undo the checks? Yes, undo those. Can I undo the X? What's happening here? Yeah, let's undo that. And that. Here we go. This is right at the point where we chose the wrong thing. And the answer should have been Y. Should have been Y. Oops, that's a line. Undo. I want to draw squiggly. Okay. The answer is when df dy is not equal to 0. Okay, let's calculate that. df dy, it's actually going to be very much the same thing. It equals 2y. It's not the same thing. It's equivalent. 2y should not be equal to 0. Okay. So now we're going to give a green check mark to any place where 2y is not equal to 0. Here, y equals 1. 2 times 1 is not equal to 0. So that now this place gets the check. How about down here? Here, y equals 0. 2 times 0 is equal to 0. So that gets an x. This is actually correct, isn't it? I mean, the correct answer is written right here. That's it. If I ask you this on a quiz or something, when can we define? I suppose what you could have done is then actually calculated df dy and said it's 2y. Anytime, you could even drop the 2. You could say the answer is y not equal to 0. That's it, right? As long as you could say 2y not equal to 0, but that's the same as y not equal to 0. But that would be the answer to this question. And at this point, y is equal to 0. We can't really define y equals f of x. So you can try, but you're not going to get it. What about over here? Can anyone tell me what this function is, what lowercase f is? So let's get an arrow. Yeah. What is the function here? F. So y equals f of x. Now let me write what f of x is equal to. What is it? Darn it, I'm not going to have a good math font here. You get it by solving for y. Solving this capital F for y, what would you get? I'm going to type it in like font. Square root of 1 minus x squared. Sorry, that's not great. Would you agree? Not only can we define y equals f of x, we can write it out for you. Square root of 1 minus x squared. That function describes the neighborhood of this point. What about now? Let's go back and Jordan made this good point. Like, hey, what about this other part right down here? That's also a different place. I would say, yeah, but that's a different neighborhood. And we can still talk about a function there, but on this side. Let's get some text. And which one is that? How would I speak of that function or type it? It's the same, only negative, right? Negative square root of 1 minus x squared. Okay. I mean, it's also a function. It's a perfectly good function. That should have been green, but you know what I mean. Doesn't matter. Okay. I like the unit circle here because it's nice to talk about it in this way. Oh wow, it's already 1:30. I spent a long time talking about the unit circle. Apologies. But it demonstrates the implicit function theorem at work. It says this point, because df dy is not equal to 0, we can define a function y equals f of x. And in fact, it's this one right here. The positive square root of 1 minus x squared is the explicit function defined in a neighborhood of this point. Down here, once again, df dy is not equal to 0. And we can define an explicit function. In fact, it's the negative square root of 1 minus x squared. That would be a description of this function down here. However, right here, there's no way to talk about a function y as a function of x, because either it'll be positive, we go up, or negative if we go down. And we somehow have to include both of those because it's the neighborhood and therefore it doesn't exist, just doesn't exist. Okay. You guys have any questions about that? I'm proud of this picture. I think it's a good picture. It's better than I could hand draw with a circle or anything like that. No more questions about this? Let's go back to my slides. Okay. By the way, this is exactly what we just did. What I have on the slide here is a description of what we just did with the whiteboard. I will say it again. Briefly, the top point of the unit circle, or if we wanted to check if it exists at there at the top point of the circle, we would say, yeah, it does, because df dy is 2y, which is 2, which is not 0. Therefore, it holds and the function does exist. Specifically, y equals, you don't have to type out sqrt for square root, because PowerPoint has a decent math font, equation editor, square root of 1 minus x squared. Okay, this is just a description of what we already did. That's why I'm going through it quickly. Now, here is the rightmost point. Once again, I've already spoken about this, but here it is written out. The rightmost point, if we tried to use the implicit function theorem, would tell us df dy is equal to 0, because 2y, y equals 0, so 2 times 0 equals 0, which says that we might not, by the way, it doesn't say we definitely don't have. Don't think of this function as an if and only if. It's not an if and only if function. Rather, it's an if df dy is not equal to 0, then there is a function. It's not saying if df dy is equal to 0, then there's not a function. It actually doesn't say that. It's just a one direction. So at this point, the rightmost point of the unit circle, this function here, the one that we had before, square root of 1 minus x squared, doesn't work. Because in any neighborhood of 1, 0, there'll be some negative values for y. And this function does not allow y to be negative, so it can't represent those points. Good. I kind of like this. I had a drawing. I gave you the drawing first and all the arrows and all the things. And then I'm giving you a PowerPoint slide, which says exactly the same thing, but it's written out. So you can go back and read it if you want. Guys, have any questions about that? 132. It's called the implicit function theorem. I've abbreviated it with this acronym, IFT. Okay, now that we're done with the implicit function theorem, let's get to the corollary or corollary. I've heard it pronounced both ways. I think I prefer corollary. I don't know what you guys think about this word, corollary, whatever. I think it matters if you're British or American. Americans say corollary because we're Americans. But the corollary is about the derivatives of the implicit function. It goes one step further to say, okay, so what? You can define a function, it exists, but what do we know about that function? And the corollary says, we know the derivatives of that function, or at least you can calculate them. You can calculate the derivatives of that explicit function, which we've said exists. We can calculate it this way. once again, let's assume capital F of X, Y, and Z is an explicit function. Sorry, that's an implicit function. And let's assume an explicit function for Z, say given by Z of X and Y, exists. By the way, what was the implicit function theorem again? It's that df/dz, it's this variable here, the one that's by itself should not be equal to 0. df/dz should not be equal to 0. Okay, so, but that's the regular implicit function theorem. The corollary says, well, if you want to figure out the partial derivatives of z, you can do that using the original implicit function. You don't have to be able to solve the explicit function z of x, y in order to calculate this partial derivative. And I definitely need to give you some examples of that, and there will be some. Well, however much time we have today, and we'll talk about it later too. You can calculate this partial derivative of z with respect to x is equal to negative. You may be like, what the heck? There's no negatives anywhere here. There's no negative here or here or here. Where does this negative come from? It comes from algebra. It comes from moving something to the other side of the equation. That's where it comes from. That's why there's a negative there, but we'll talk about it. It's negative of the partial derivative of the initial f with respect to x. That's the one on the bottom, over partial derivative of f with respect to z. That's the one on the top. So it flips here. The z is on the top, but it's on the bottom. X is on the bottom, it comes on the top, and there's a negative sign. But that's what the IFTC is. It's that there's a handy way to calculate these partial derivatives if they come from this implicit function, simply by taking negative the fraction whose numerator is the partial derivative of f with respect to x divided by partial derivative of f with respect to z. And each partial derivative should be evaluated at this point, x, y, z. Remember, implicit functions are funny in that they could be, they're really just defined in terms of neighborhoods. It's a little bit too much light. So really you're talking about what's happening in the neighborhood of this x, y, z, x prime, y prime, z prime. And if you want to know these partial derivatives, well, they should also be evaluated at this point, x prime, y prime, z prime. Because if we chose a different x prime, y prime, z prime, we'd talk about a different neighborhood, something totally different could be happening over there. And in fact, you could think of that like, you know, the circle, the top of the circle versus the bottom of the circle. Something different is happening, you might think. Okay, we need some examples of this. Here's a simple example. In fact, it's exactly the one that did I leave it on my whiteboard? I think I did. We already showed that given this function, an explicit function of y exists at the point 0, 1, but not at the point 1, 0. Let's now use the corollary to find dy dx at the point 0, 1. I'm sorry, I wish I hadn't given you this answer here. Don't pay any attention to the answer. Let's go to the what's it called, whiteboard, and calculate the answer there. So now, this question was the initial, where's that? The initial question. I don't care about this point anymore. I care about this point, the green check. And I actually don't care about this point either. I will leave this df dy, but the new question, it's like a second question, and that is when, I'll just draw it here. You know, the next, oops, I want it to be black. The question is find, you could actually find this really easily, but let's pretend you couldn't. Find dy dx at this point here, 0, 1, at 0, 1. Let's find that point. Okay, so the corollary of this theorem says, I can find this value, dy dx, by looking at the partial derivatives of capital F. I've already given the partial derivative with respect to y here. We've written it out there. let's now do it with respect to x. Sorry, my mouse is sometimes jumpy. What would it be? I'm just going to tell you because it's obvious, 2x. So the partial derivative with respect to y is 2y. The partial derivative with respect to x of this original function here, by the way, is 2x. What does the IFTC stand for? What does it stand for? It stands for implicit function theorem corollary. But what does it say? It says that dy over dx is equal to, remember what it said here, there's a negative sign and it flips. If you remember that, you're good. Anytime I give it to you on a quiz, you're not really probably going to take a lot of timed quizzes in this class, but maybe, yeah, maybe you might, I guess, like some in-class quiz or something. I give you an in-class quiz and there's a question about the implicit function theorem corollary, and it'll save you some time if you just remember the way to get this is to remember they both flip. The y and the x flip, and it flips from positive to negative. I mean, assuming there's no negative on this side, but there is a negative on this side. So what would it be? Negative fx over fy. That's sort of the answer. Of course, we haven't evaluated it yet, but fx is 2x and fy is 2y. So this becomes negative 2x over 2y. And then what do? We evaluate it. When I say evaluate, it really just means plug in the point x equals 0, y equals 1. If x equals 0, y equals 1, this becomes negative 0 over 1. It just becomes 0. And, a big surprise here. All I've said is that the slope of this point is 0. It's like the most obvious thing in the world. You didn't need to do all this calculation to tell you that the slope at this point is 0. And that wasn't the point of this exercise. It was to demonstrate in a very simple and perhaps obvious way that this way of calculating derivatives, or sometimes it's partial derivatives. Here it wasn't a partial derivative because y was just a function of x. However, if there were more dimensions, like there were z in here, you could imagine y being a function of both x and z. In which case, if I wanted dy dx, I would write that with curly d's, because that would be a partial derivative rather than a total derivative. Here's total derivative. You just call it derivative. Okay, so it worked. The IFTC worked. It gave us this answer. By the way, this would work for any point on this curve. If I wanted it, what's an interesting point on the unit circle? I think this one is, this is x equals 1/2, y equals radical 3 over 2. If you wanted to know the slope at that point, it would be negative 2 times 1/2 over 2 times radical 3 over 2, which is actually negative, why am I blanking here? 1 over radical 3. You basically get back the trigonometric identities here of sine, cosine, and tangent. That's what's going on here. Which we don't need to bother with. I'm not here to teach you about trig functions, but I did just want to demonstrate that, hey, this formula here, what's the key takeaway is this. Oh, it's a circle here. This formula is what we get from the corollary, and it always works. It doesn't just work at this point 0, 1. It works at any point. Oh, by the way, it doesn't work here, right? It does not work here. What would happen if you tried to use it there? You would get a 0 in the denominator. You get negative 1 over 0. The universe explodes when you try to divide by 0. That's what internet memes have taught me. So yeah, this can only be used when df dy is not equal to 0. That's why it's a corollary, right? That's what corollary, by the way, do you guys know what corollary means? It's like a additional true fact about a theorem that can only be useful once the theorem has been satisfied. Like here's a theorem that says something about something. Oh, by the way, there's an additional corollary that says, well, once you've gotten all of that out of the way, you can learn a little bit more about these objects using the corollary, and that's what's happening here. Okay, I think we're about out of time. You guys have any questions about this? It is a lesson on implicit functions, what they are. Anytime you have a relationship, you can always create an implicit function, and it can be capital F equals everything that's not 0 on the left equals 0 on the right. And that will define some relationship of x and y. It may or may not be one function one variable as a function of the other. The implicit function theorem tells you at least when it might be true. And the implicit function theorem corollary tells you something about the slope or the relationship between these variables y and x using the original formula for the implicit function. I guess that's really all we did today. But let me know if you have any questions. Let's talk about what we will do next class. I think we should talk about the midterm if you want. I'm happy to do that, which means I want to get your midterms graded and back to you by then. Otherwise, we'll have the same problem we had today. But so that's my goal, is to get you guys some feedback on your midterm and answer any questions you have about that. That probably won't take the whole class. I'm not predicting it will take the whole class. And then once we're done with that, we'll finish up talking about implicit functions. And I'll also get you some homework on that too, so you can have some practice on implicit functions.